It's my pleasure to introduce Abhi Shelat. Abhi is a professor at Northeastern University. He also works at Google right now. He is an author of many exciting works, very relevant to our space, including RSA setup ceremonies and most recently ECDSA signatures in a threshold setting, which are kind of the fastest right now for multi-party cases. So a lot of companies are trying to deploy them and use them in production. And Abhi is going to talk about that today.
Thank you. Thank you, Lair, for inviting me here. It's been a great week here. I'm also, you didn't mention, I'm a budding stand-up comedian. So I hope to share some of my comedy about ECDSA with you today. And this is joint work with my three students, Jack, Yash, and Eysa, which have been just fantastic. Many of you have asked about academic careers, and I think that's like the best, finding great students you can continue to work on with years that drive you. That's really great. And these slides are a combination of work that was done by these three people that I have just edited and added my stand-up comedy to. So yesterday, Chelsea mentioned, or 2 days ago, Chelsea mentioned why Schnorr hasn't taken off, even though it is cryptographically elegant construction and so forth. And I found the reason. It's this patent right here in 1991. The patent, if you just look at the first pages in the diagrams, they sort of talk about like this Schnorr-style proof in the discrete log group. But right there at the bottom, like claim 9 essentially also claims doing all of those methods in any elliptic curve group. So this was 91, well before elliptic curve cryptography had taken over, but still he was smart enough to patent that. So that is what has messed up, I think, all of the cryptography of the last 40 years, 33 years. As a result, Scott Vanstone came up with this ECDSA, or DSA, and I guess ECDSA to overcome those issues. And this has a number of problems that are very hard to model cryptographically. So the first problem is, although this equation looks pretty tame, it's doing a lot. When you write it like this, you sort of elide all of the group structure. And so R right here is an elliptic curve point, right? So it's an x comma y. It's like a point like that right there. And now you use the x coordinate of that R inside this equation. And this equation, again, is a different field than this elliptic curve field. So this right here is in the field, this right here is in the order of the group. This number is between 0 and the order of the group. And this number right here is between 0 and another finite field, which is not related to the base of the elliptic curve group. Does that make sense to everybody? So essentially it'd be like you're taking, so this right here is a very, very crazy operation, because although it just looks like a multiply, you're casting a number from this range into a number to this range, and you're just sort of like, and that's very hard to, go ahead?
But this is something that I always have a hard time wrapping my head around. This is not ECDSA specific problem, right? This is DSA problem, because even in the original DSA problem, they were mapping the guy from the group to the guy from mod P, mod Q, right?
Yeah.
And so it is, I agree with you, a crazy operation to do, but it's not specific to the elliptic curve, right? It's just this mapping from the curve to the field.
Well, no, the elliptic curve thing is, in the DSA at least, you're talking about scalar values here. Now you're talking about R,
talking about two
X value of the R.
You're talking about one or two scalar values. I mean,
okay.
I don't know. I don't see why ECDSA, in my mind, ECDSA does not introduce any
things that DSA, they're not present in DSA. Yeah, sure.
But I don't know.
But, okay, fine, but then DSA still has this problem, right?
No.
Yeah.
That's, I'm not questioning that part.
Okay, and of course, if you remember the equation from Schnorr from Chelsea's talk, the other big problem here is that K appears in the denominator, so there's a multiplicative inverse. So these are really the two difficulties. These three values of K have to be consistent throughout this equation. That's what makes creating a threshold version of this function very difficult. Unfortunately, so when you're faced with things that are a little bit of a hack, you could choose to ignore them. And you can't here because this is pretty widely used, all of these companies, all of these protocols and so forth. And I did a little bit more research. I was intrigued by this. So for example, these two curves, which have been used in crypto for quite a while now for signatures and so forth, you can't actually, Let's Encrypt doesn't issue certificates with curve 2559 or curve 448. In other words, not only is like ECDSA wired in, but also the curves for ECDSA are wired in. You can't even use it on different curves. You can't use different signature schemes that are, that have more better security proofs. And the reason, so for example, Ed right here, you see this person who's on Let's Encrypt staff explains why, even though there's a lot of analysis behind this curve, it's not a prime order curve, and there's some crazy stuff, and NIST curves have this, and like, as a result, I don't want to do it. And I work for Let's Encrypt, so I make the decisions. So there's another thing called the CAB forum, and these people basically give recommendations on how websites should run, how like big websites should run. And in their baseline recommendations for TLS security for big companies, they have this thing where they say, essentially, you can only use RSA or ECDSA. And if you use ECDSA, you can only use these versions of this. So the world has been locked down. And philosophically, I don't know how to react to that. Is that a good thing that, there are only 4 options and we're stuck with that? Or, I don't know. So we come back, we face the difficulty here. Because ECDSA is so widely deployed and so ingrained in the way that people are going to operate for at least the next few years, then we should tackle the difficult problem of how to make a threshold protocol, which I've skipped. I've assumed that you remember everything from Chelsea and you and other people's talk about what the model of threshold cryptography is, etc. For people online who are just seeing this, you'll have to go see their talk first, and then you can watch this one. Anyway, so I want to get to the point. I have a few points, technical ones, that I want to get into. So that's that. What is the difficulty? There's no simple linear decomposition of these things, so you have to use some more advanced protocol. Whenever you encounter something messy, sometimes you have to look at the master of tackling big messes. And so I kind of like this one the best. Very, very messy situation with all those impediments, and boy, just curves it. But the other 11 examples are also of the similar ilk. So whenever you're faced with that sort of complexity, maybe you could find sort of a play that would be worthy of dealing how the maestro of messiness deals with other things. So that's what my plan is today, to basically, if you look at this, there are many, many prior works here that have handled ECDSA, threshold ECDSA, and many techniques and so forth. And I want to try to build a framework for reasoning about all of them. And I think there are only 3 different type of ideas for how to tackle the messiness of threshold ECDSA, which I hope to basically abstract. And then all of the other differences between these 20 works, they all basically are what I consider to be lower level choices. So the choices of how you implement a multiplier, the choices of how you implement the consistency check. So with those 3 things, I think you can basically characterize all of these prior approaches. How you handle the messiness of ECDSA, and that we consider how you algebraically rewrite the equation, how you handle multiplication for these things, and how you handle a consistency check. So that's if you can pull out exact components, and you can then basically see that this right here is just like a ad hoc exploration of that tensor product. Everybody's basically found different little things and like written a paper. And so there, once you do that, you can try to put together the best pieces, and then that is what I think the 3-run protocol that we've written about. That's what I feel. That's how you should. That's how I look at that work. So, of course, there are many different settings here. The honest majority setting, where you can assume that more than half of the parties are honest. That's a different setting. We're not going to talk about that today, but there are many works and techniques in that I will bring up. And then there are 2-party cases and multi-party cases, and then there are generic techniques versus like more specific. But I hope to try to explain all of this prior work along those 3 dimensions right there. So let's start with that. And of course, the first dimension that I mentioned, this common pattern, is that, unlike Schnorr, which is just linear combination, here the ECDSA has to compute this K inverse. okay? And you can't do it as an arithmetic circuit over, you can't represent it as an arithmetic circuit, it's too expensive, or a Boolean circuit, for example. So everybody, all these efficient protocols have basically come up with special ways of doing that. And I think there are only 3 ways that, and even once you look at this, you can try to think of other ways. I don't think there's much space there, but of course, this is where there would be some improvement if someone comes up with some better way to do this. So as I mentioned, the recipe is figure out how to rewrite this to deal with this inverse, figure out how to do multiplications that you can do with a variety of ways. You can use pi-a or additive homomorphic encryption, or you can use sort of OT-based multipliers, or you can use class groups, or you can use other techniques, PCGs, you can use a number of techniques to do that. And then, of course, consistency check. So the first approach, I want to give you an example of what it means to do that first rewriting of ECDSA. And this first approach was like Langford, 95, and also Rosario and his co-authors in 96. They were working in this different model of honest majority, but they actually, this technique of inverted nonce rewriting is how we call it, is due to them. And so here's the observation. So what you can do is, instead of having k inverse in the second equation and k up there at the top, you can of course flip that. That's this equivalent way of rewriting that, right? And now, right, so that right there has changed S now from this inverse into just a secure multiplication, with the problem being pushed to this creation of the value R with that particular structure. And for that, they used this Barillon-Beaver trick, or BB trick, that many, including our results, use this trick. And I'll just give you a short example of how that works. So what you do is this is a very nice trick, and we talked about it on the board yesterday. I think it has uses for all sorts of credentials. A very simple trick. You sample another, you secret share with this bracket notation, is the standard notation in this field for secret sharing. It's like a compact way of saying that. You secret share a phi, then you reveal you do a multiplication between these 2 values and reveal that publicly. So you reveal the public value there. You also at the same time reveal phi time the scalar product of the group element G in phi. And that's kind of like what Yuda was talking about yesterday. That's kind of the bread and butter. There's several commit and reveal type of protocols for that. And then now, since this product, the first product has been revealed, you can kind of compute the inverse in the clear. Everybody can basically compute that inverse and then raise it to this value phi. And if you just do the math, right, these phi's will cancel out, and you'll basically get k inverse times G, yeah? Everybody see that? I try to make the equation simple enough so you'll remember how this Barillon-Beaver trick works. Okay, great. So that, as you can sort of see, the nonce is k, that sort of thing. And you've basically inverted the nonce. That's why we call this the inverted nonce technique. And no matter if you try to look at those 20 papers, it might be hard to extract what they're doing because, again, they're going to focus on exactly what they use for the multiply, or what ZK technique they use, or how they avoided a ZK step from a previous technique and so forth. But ultimately, it's very hard to extract this, but all of these works right now. What I want to do now is basically walk through all of these particular papers and kind of explain what technique they're using and where these ideas came from. And then I think you can basically select the best of all of these, and then you'll end up with the protocol that I think we've ended up with. Okay, so that's the inverted nonce technique. So the second form of rewriting I'm going to talk about is the multiplicative form of rewriting, okay? That's essentially doing something like this. And so essentially what you want to do is set up multiplicative shares of sk and multiplicative shares of k. What does multiplicative share mean? So additive share, normally you know that I have a1 and you have a2, and then the product, the share, is actually a1 plus a2. Multiplicative shares means that the thing that we're sharing is the product of our shares. And when you have multiplicative shares, if you look at this equation, just to keep you all with me here, what does that help you do? If you have multiplicative shares of k, how does it help you solve this equation?
We take inverse and then multiply?
Yes, right. So if I have k1 and you have k2, then we can locally compute the inverse of k1 and the local of the k2, and then we can actually basically have multiplicative share of k inverse, and then of course, then we can multiply it by a, and then basically have multiplicative shares of a and multiplicative shares of this term right here. And now you need a protocol that go from like multiplicative to additive shares. And that's the protocol. So everything you do locally, you do one protocol, which turns multiplicative to additive shares, and now you have additive shares of S, and now you continue to do the reconstruction as you prefer. And so this idea we first find in this McKinsey Ryder paper. And then Rosario and his co-authors, they came up with a version of this using threshold pi a, and that had a certain number of rounds, maybe 8 rounds, and then the Bonnet paper basically reduced the round complexity, if I'm correct, roughly like this. One problem with these things is that they relied on this threshold version of pi a, which immediately, so during a setup, you are required to have a threshold share of a pi a key. And that's a very hard object to create because essentially a threshold key is like a RSA modulus for which nobody knows the secret keys. You have threshold versions of the secret keys P and Q. And as Lara mentioned, I've worked on that problem, and we've implemented a version of that protocol which has been run, but it's a complicated protocol. It's something that if you can avoid, it's better. And in fact, Yuda, in 2017, he does avoid this. He does avoid the threshold, but only because in this case, his protocol only works for 2 parties. So in that case, one party can actually have the threshold key, and that's how they avoid it. So all of these protocols are basically different variations of this and then of course our protocol from 2018 and 2019, we essentially replaced the pi a part with an OT, and we also have a different consistency check, and together we can make that more efficient. But we were basically using this rewriting mechanism for that technique. For 2 parties, this is great. This multiplicative sharing is very easy to do. In our 19 paper, when we do this for many parties, we get increase in number of rounds. The version of our paper that we published had like log t plus 6 rounds, and then we were able to reduce that to 5 rounds. But still, this sharing was very hard to deal with when you're dealing with multiplicative shares. In terms of history, then Rosario and Goldfeder, they were able to go back to their 18 and 20 papers, I view as going back to the inverted nonce. You can object to this, but this is how I look at your work. Going back to the inverted nonce technique, and as a result, they can get rid of the threshold pi a version of the assumption right here. So see the machinery, all you need is pi a for this. And their first version of their protocol, I think, again, has like 8 rounds. And then CGG-MP is able to reduce that basically. So the first 3 rounds of GG, of both GGs, basically are the first 3 rounds of the original inverted nonce, the GJKR paper. That's how I look at it. And then the last 5 rounds of GG are essentially the consistency check, this like masking technique that's used for checking for consistency. And CGG-MP, the Canetti et al. Paper, they basically reduced this now from 8 rounds to 4 rounds, or 4 or 5 rounds, I can't remember. But essentially, they do this by replacing the consistency check with the generic ZK check. So it's a very expensive ZK check, but it reduces the round complexity. This is how I interpret this work. And this is now towards the final end of the work in this area. So Yuda and Ariel Knopf, they first wrote a paper in 18, and then it later got, the journal version of it included Iftak and Samuel. Both this paper as well as the next paper, the Abram et al. Paper, they both used this new rewriting called this ECDSA tuple. I'm going to work through it in a second, but it essentially uses this Bar-Ilan beaver trick twice. And that rewriting, that has a very, very simple algebraic structure for the rewriting. And that, I think, is actually great. Now Yuda and, so LN was pi a based, and then they later replaced it with an OT multiplier. But the pi a based version of LN still required these like zero knowledge range check proofs and a complicated consistency check. And same with this paper. This paper basically they require. So this is why they needed to come up with a very simple rewriting, because they're trying to use these pseudo-random correlation generators to get a very, very low bandwidth protocol. So it's like on the order of 100 bytes sent to do this threshold signature. However, the computation is like really quite big, and the implementation, the setup for this PCG is something that maybe it's too complicated to implement.
So then later is a multi-party, 2-party?
Yes, the this ANOS paper is multi-party, and the HLNR paper is also multi-party. And there are other generic techniques. So in particular, Nigel and this DOKSS paper, both of them basically observe that you can use speeds generically, and you can basically do these Mach checks in, you can do speeds with Mach checks in the exponent, and that is a way for basically implementing any threshold thing. But they have their disadvantage. In particular, the bandwidth and the complexity of their protocol basically is, their consistency check is too expensive. So let me try to summarize all of these techniques. This is essentially how I view all of the prior work. You look at how they've rewritten, and there are 3 ways to do it. You look at whether they're using OT-based multipliers or PyA-based multipliers or other techniques for multiplication, and you look at how they do the consistency check. And you can use, for example, generic ZK proofs. You can use some sort of check relations in the exponent like we've done. You can use generic Macs from Secure MPC. You can use any sort of Mac. All of these things basically go to the efficiency. And what I'd like to do is show you that in our paper, these are basically the negative downsides of each of these particular approaches. And what I'd like to basically show is that what we can do in our work is we use this ECDSA tuple rewriting, which I'm going to work through. You can use any 2-party multiplier as long as it's a secure multiplier, not a leaky multiplier. And we implement that using OT because we think that's a great decision. However, you can implement our protocol with any multiplier. So for example, you could use a secure PyA multiplier. That secure PyA multiplier would still need to use these ZK proofs for the range checks and so forth, but if it did a secure multiplication per like some ideal functionality, that would work. And then our verification, I'm going to show you this like statistical check. And the basic idea is this. We're going to exploit the fact that you basically have commitments. The public key is a commitment to a secret key, and the nonce is a commit, like the public nonce R is a commitment to R, to K. And since you have these public commitments of these values that are already ready for you because of the problem definition, we're going to exploit those, and we're going to create a very simple Mac that we can use to check consistency of all of these equations. That's a statistical check, and that basically requires no extra, like very little extra work to actually implement. Now, that's the high level. If you actually look at our security proof, there are 3 small modifications to what I've said to deal with very small technical issues, which are not worth, so it's not, our protocol is not exactly as I've said in this way, but close enough. Okay, great. So let me talk about this ECDSA tuple rewriting. So this is our original equation, you see. And so here is this double Barrelon Beaver trick. So what you're going to do is as many, just like the first inverted nonce writing, you're going to sample this phi value, and that's going to be an extra secret share. And the trick here is to multiply this S equation by 1 in the form of phi over phi. The secondary trick is that if you have a way of computing this alpha and then you have a way of computing this beta, you can just do alpha divided by beta, then you can basically compute the signature. And of course, this is uniform, beta is uniform. You can reveal it publicly because of course it's masked by phi. And then alpha is basically fixed by what the signature value is. So it's just a slight difference from the original inverted nonce technique. And the main point here is that now, essentially, you have a multiplication of k times phi and sk times phi. Yeah?
Are those 2 different secret sharings of phi?
No. Well, that's, so in our implementation, yeah, that's right. It is the same, it is exactly the same secret sharing of phi. And then I think your follow-up question might be, then don't you have a problem of maintaining the consistency of the value phi in both of those multipliers? And yes, you do. And there's a pretty simple way to get around that, which I'll get to in a few slides.
Yeah, and secrecy if it's like a one-time pad type of...
Yeah. So you're only going to, you're not going to ever reveal phi, you're just going to reveal alpha and beta at some point. This right here is what we call this ECDSA tuple. So sk, of course, is shared before during the setup phase, and then k, phi, k times phi, and sk times phi, that's the correlation that you basically want to create, and that's the correlation you want to check the consistency of. And notice it has more redundancy than the other versions of the rewriting, And that redundancy lets you do these checks, like for example, our consistency check in a uniform way. LN does not explicitly explain that they're doing this. They are a two-party protocol with using PyA to do threshold ECDSA.
I thought LN was multi-party.
Yes. Yes. So, yes. Yes, you're right. It's a multi-party protocol.
Are they doing, is the second one doing OT?
The second one is using a PCG. So the second paper, their main goal is to explore the extreme version of like, if you needed to only send a few hundred bytes, could you achieve this? And as a result, it's essentially they have this big hammer of a PCG, and they're basically showing that you can apply it to create these type of correlations. So PCG is pseudo-random correlation generator. And as a result, they identify that this is the correlation that you need if you have this correlation. And so, yes, I would credit Abrams et al. For writing down this as being the correct correlation that you need to do. And then we observed that this is kind of also implicit in what these people are doing 4 years before. So clearly there's like a subliminal influence in how this is working. And we would like to explicitly credit them for that great idea. Here's how we do our three-round protocol. In the first two rounds, you're going to use the standard technique that Yuda talked about yesterday for, in parallel, establishing that value R, and then also securely computing these two particular values, k times phi and sk times phi. We're going to set up the part of the verification of the consistency, and then in round three, after those checks pass, in the middle here, you locally compute your local share of this alpha, and then you basically reveal these two to the party that's reconstructing the secret key, and then given that, you can output the signature like this. We run this standard protocol, which everybody could reconstruct from imagination. This is the secure multiplication protocol. And you'll see that the fact that we use phi twice here helps you helps you with the consistency.
So this is T out of n.
This is T out of n, yeah.
Then how do you sample the T out of n shares of random values?
Well, so this is the signing part of it. And so essentially SK has already been set up as a, and then this this is just T out of T actually. So you can apply your Lagrange coefficients so all of this will just be additive shares at the end. That's the folklore, that comes from their basic observation. There are many methods to do the secure computation. We're going to promote this OT-based one, which we've implemented very carefully, that works extremely fast and has reasonable bandwidth. And then this new consistency thing is the simple check that we've contributed to this literature. Okay, very good. This, by the way, so when it is a T-party thing, of course, you do these pairwise multiplications and then sum them. That's kind of what this equation is saying. So essentially, this protocol is what every party does with respect to every other party. So it's pairwise versions of this thing in parallel. How do we do the multiplication? So our abstraction is this two-party multiplier, which Alice and Bob basically put their inputs A and B, and they get output C and D such that C plus D is equal to A times B. So we're going to do one small extension to this, but we'll treat this as kind of like a basic maliciously secure building block. That's what you have to basically provide to instantiate this framework. We can talk about how you implement this with OT as well. So here is the one observation, that our protocol requires you to securely compute K times phi and SK times phi. And those are two multiplications where one party has the same input. So diagrammatically, this picture looks more like this, and essentially one party has one input, the other party has two inputs, and each party basically gets additive shares of the both, right? This is one of the benefits of this, writing the correlation this way already lets you solve one of the consistency problems with this, because we call this abstraction, essentially. We get this consistency for free if instead of a multiplier, we call it a vector multiplier, right? Or vector oblivious linear evaluation. Volley is kind of the same thing. And when you do this with an OT multiplier, it's like almost comes, it comes very easily. Not for free, because you're doing less than twice the work of one multiply in order to get two multiplies. And you also get the fact that by the structure of the protocol in the case of OT, if you use like random OT in, for example, then this B right here is like already by the protocol fixed to be consistent for both multiplications. So that's a cheap idea. If you just use vector OLE as your primitive for this multiplier, then you're forcing one of the parties to use the same input for these two multiplications. Now I want to talk about our consistency mechanism. As I mentioned in the sort of introduction, we're exploiting the fact that this protocol, this problem, has a bunch of setup that already that we get for free. So first, as you know, since it's a threshold signing key, the public key exists and everybody knows it. And during keygen, everybody has a share of SK, but we also have this MAC, this commitment to essentially this secret key sharing. And of course, part of the protocol requires us to basically share this R, and that we also have as kind of a commitment to some value of K. No other protocol is exploiting these two values. That's one of the big differences. No other consistency check. All of them use basically the generic hammer of GMW style ZK or explicit max, and both of those are basically doing more work than necessary. That's our main point, is that we can use these two to get a simple check. Another way to look at it is that we're basically going to interpret this value phi that we've sampled for this particular protocol as a distributed MAC on K and SK that we're going to check in the exponent. How do we exactly do that? One other fact that we're going to need is, like yesterday when you saw this talk, you saw that the standard way of reducing this R basically has everybody basically publishing this value Ri, which is their local Ki to the G element. And so this is an artifact of that nonce creation protocol, and we're going to exploit that as well. So let's see, just as a two-line reminder of Uther's protocol, everybody first commits to their value, and then after receiving everybody's commitments, you reveal the commitment. And just to hammer this point, why do we do this commit and release? This is a test. You saw this talk yesterday. Why do you do this commit and release, any of the students? What was the thing that you're trying to avoid? What if we just release it? This is a fundamental attack he was defending against. So what if everybody sends, your first message is send Ri, which is, your local Ki times G. You're supposed to publish that. What goes wrong?
The Ross attack, right? Not.
Maybe, but there's a simpler attack, simpler point that he was making.
Concurrent?
Making it zero, like the adversary can sample the key.
Bias, yes. So essentially a rushing adversary can listen to everybody's thing and then decide what they're going to send, and you can cancel out people's shares and bias the key to anything you want, in particular a key that you know exactly the thing to, right? So that's why you have to do this in two messages. And his, of course, major trick yesterday was this EVRF to get rid of that by forcing the adversary included to essentially have already committed to what they're going to say. Now, I thought about, later on, I'll show you in the protocol, I thought about using his technique. You'll see why it doesn't necessarily work in our protocol, or at least I don't yet see how to do it. Anyway, here is the nutshell idea for how our consistency check works. If we look at this version of where we are right now, we know that at this point, Bob has published this value RB. Bob is supposed to put, this is the multiplication between phi and k that we're doing. We also have to do one between phi and sk, which will work exactly like this. Remember, our special abstraction is that we're using this two-party multiplier. So Bob puts in his share of kb, Alice puts in her share of phi a, and they're supposed to get these two multiplicative products. Now let's just work out essentially so if you plug those in, essentially this is the equation that we get, right? Now let's work out exactly what we know and what constraints must hold, the invariant that must hold after this multiplication. The first step is we just rewrite this. So we know that essentially Bob's output right here basically has to satisfy this constraint here. Everybody also knows essentially Bob's public key there. Okay, so if we define D here just as Bob's output to the G there, I'm going to claim that it is okay for Bob to send this value D over to Alice. So it's kind of like a one-way function. This is like a scalar one-way function of Bob's output. I'm going to claim that that's okay to send. Here is why that's okay. Remember, I told you that everybody has RB, which is just KB to the G, right? And Alice already has phi A, right? So if Alice takes RB and raises it to this phi A, right? That's basically G, that's basically this product right here, right? G times this product. And of course, Alice also has C. So if Alice basically subtracts from this product C times G, let's call that T. Now, what is the relationship between T and D? They should be equal. If Bob hasn't cheated, then T should basically be equal to D. And so Bob sending over this value D essentially shouldn't give, if Bob hasn't cheated, doesn't give Alice any extra information about anything. Okay, so that in fact is our consistency check. That's, as I said, there's two other tweaks that have to be applied to this for slight re-randomizations, but this is the heart, so you can't apply this directly, but this is the heart of it. So Alice is going to, because this value is floating around already, Alice is going to have a way to check. So Bob is going to get an output. Bob is going to compute a one-way function of his output and send it back. And if Bob hasn't cheated, then these two values have to be equal. What happens if Bob does cheat? All right, so let me go through that. This is exactly what I just basically said. If Bob is honest, then these two have to be equal. Alice can compute the thing herself, and so thus sending this doesn't leak anything else. That's a perfectly safe check. Now, what happens if Bob is malicious? The way you can model that malicious behavior, right? So either Bob sent some value here that was, Bob sent a value here that's not the input that he's using in this multiplier. And the way that we're going to model that is to say that this input right here, we're going to call KB, and this value is to where he cheated. Instead of sending this value, he sent some other elliptic curve with some offset delta. Okay? So what happens now when essentially when Alice now computes this, here's the highlight. When Alice now applies this function T, when she computes this T using this particular equation, there is going to be a component of this value T that Bob is going to be very unlikely to predict. As a result, this check is going to fail with very high probability. Essentially, this is the fundamental inconsistency that everybody knows this value. It's different than the actual value that's defined based on Bob's input to the multiplier. So if Bob's dishonest, this first value D is based on what Bob can compute, right? So Bob put some particular thing in. We rewrote this right here, right? We rewrote the equation D and we just substituted it right here. The value that Alice computes is this value. And so all I'm going to do is expand this second equation right here, right? Substituting this value of RB for this value of, essentially RB is this value right here, right? You can essentially, this multiplication right here is basically going to take delta and raise it to the phi A power right here. And so this offset right here, delta, some unknown value that maybe Bob controls, right, is going to be raised to this particular scalar element, and is going to essentially be a random group element that is added to the rest of this equation. And so for Bob to pass this check, Bob has to send over essentially the D that they was able to compute based on his view of the protocol plus this value right here. And this is why we call this value a MAC. It's a MAC in the exponent because Bob has is information theoretically hidden from Bob's view. If we treat multiplier as an ideal primitive, then phi A is information theoretically hidden. It's a MAC key essentially on this value. And so his probability of succeeding with this is essentially the field size, the size of the MAC. It's a statistical check as a result. So no, that's a pretty simple idea, right? It's not zero knowledge, it's not a big hammer, it's not anything. It's just extracting the fact that when this term in the exponent basically is there for free, you can basically check the MAC in the exponent essentially for free. And you can do exactly the same check. you can do exactly the same check for the phi times sk multiplication. And right, you use a vector Lee for that multiplication and essentially the same exact check. This is ultimately what our protocol is. Now you can sort of see why this primitive from yesterday, which helps reduce, so this primitive basically is a generic way of taking any protocol that has these two steps and squashing them into one step. And so when we apply it to our protocol, we can squash these two into one round right here, but our multiplier still requires two rounds. And I don't know how you can basically predict how you can commit to, well, this multiplier is not of the form I first commit to something and then I send something. So I'm not sure how to apply his technique or how to move that first multiplier message into some sort of pre-processing state to improve that. So I don't think it improves our protocol from 3 rounds to 2 rounds. However, I do think our protocol can be pipelined in order to achieve the 2-round thing, which I'll talk about in a second. Anyway, this is the version of our protocol. Everything is quite cheap and quite simple. And this pipelining idea, I think there's nothing clever about this, but the observation is that this message right here and this message right here, they can be produced without any knowledge of the message. And so you can basically send that first message with the last message of round 3. What this requires every client to do is just keep the state of that message, and then during the online phase, then these two messages can basically be exchanged. So this is how I think you'd get the same performance. And because our protocol is UC secure, one can basically agree that this type of composition is okay. Last little detail here. This slide is about how you can realize the multiplication technique. So far I've said the rewriting technique you should use is this ECDSA tuple idea. The consistency check is the one that I just explained. It has no zero knowledge, does not require simulation extractable zero knowledge or range checks or range proofs or any sort of consistency check other than what I described plus 2 small tweaks, which add a few operations, but constant number of operations. Now you could basically pick what multiplier you want to use. So pi has, so if you want to implement this 2-party vector multiplier, this vole, essentially you have pi class groups, these PCGs, and oblivious transfer. And they have their pluses and their minuses, all of them. Some require specific assumptions. Some require internally, inside the multiplier for proving malicious security, you need like a ZK proof for the pi or class group proof based schemes. For PCGs, you don't. And for oblivious transfer, you don't. And you can build these from most public key assumptions, but these other ones require specific assumptions. And then it comes to performance. So essentially, in terms of compute time, right? So there isn't a line here that basically says how much does the communication cost. So pi has very small communication, but still on the order of kilobytes for a multiplication. Class groups have a lot of communication, I believe. PCGs are very inexpensive individually, very cheap amortized, but you have to amortize them in batches of 100,000. And oblivious transfer, I'll give you some details about our performance and our implementation in a little bit. So we do these experiments where we put these nodes in like GCP data centers. These are the ones we use for this experiment, and these are the times that we were getting. Some people say these are slow, which I agree, but these are literally the times we measured, so we might not have been on the right virtual network or the right instance type, but that's what they are. So we only compared our technique, our new technique, against our previous technique, the one from 2019, and then we found an open source implementation of CGGMP, but it was by Taurus Group. But we weren't able to get it to fully, it wasn't networked, so we weren't able to run apples to apples tests. I'll show you the tests we were able to run. But it should give you a sense of what the trade-offs are. So it's a big, big table with lots of data that I copied and pasted from our paper, but I'll highlight some of the points here. So in terms of 2, 3, 4-party signing, again, we're like 4 milliseconds, 6 milliseconds, 8 milliseconds for the signing part with our newest signing approach. This is faster than our prior approaches. Since our technique only takes 3 rounds, as soon as you start testing on wide area networks, the US, like across across the country or across the world, then these numbers become like really quite big. It's like 105 milliseconds to go cross country, essentially for the 3-message exchange. And so you can even see that like when we're up to 256 parties, we're still signing on the order of a second, which is reasonable. And our setups are also quite inexpensive. And then we basically compare our bandwidth right here. So for 2 and 3 parties, it's like roughly, it's about 53 kilobytes essentially per party. So that's kind of like the gap here. So it's about this, it's way less than what people send on Snapchat to each other. So as a result, I consider it reasonable and conceivable for the signing. And then finally, in this last corner, I know this isn't the best implementation, but it's the one that we're able to find. And we ran just compute only, so on the same machine, and just for 2, 4, and 8 participants. And the signing and setup times are already like in the thousands of milliseconds, or like in the seconds. So there's a big gap between essentially all coming from this particular framework. As theory predicts, you know, for like essentially a 6 times improvement from our own signing from our 2019 paper, based on the fact that we're now a constant number of rounds, 3 rounds, as opposed to, we didn't implement any of the pipelining in this experiment. So I think that is all I want to say about this. Any questions?
Sorry, do you mind just saying, like, recapping intuition for why the multiplication needs 2 rounds?
It's based on OT extension, and the best you can do in OT extension, well, PCGs are a way around this, but like using standard OT extensions, which we're doing, they require 2 rounds. Okay, so to answer your question, why is it 2 rounds, is because that's a fundamental limit that we get from OT extension, that the online OT extension is like, so we did a bunch of OTs, and we did a bunch of, you know, setup and so forth, and now we need to extend those OTs, and that still takes 1 sender to receiver exchange. So that's where that, and then that's all we need. Once we do that, we can de-randomize the OTs, and then we can use them, interpret them in the right way as multiplier values. So I don't see us getting around that. The PCG technique gets around it. That allows non-interactive OT extension, right? But that data point shows you that it's feasible. However, and this is from my memory, so for example, for the value of 80,000, which I picked out from their paper because they're 80,000 seconds in a day, it takes them roughly 80,000 seconds to pre-process 80,000 OTs. So essentially, if they were to use that in production, you'd basically on Monday be having to do all of this work in order to basically do 1 per second on Tuesday. And so the online phase of their thing is very fast. It's only like 5 milliseconds per multiply. However, the offline phase takes 1 second of computation per multiply. So bridging that gap would be the thing. Like right now, we don't do anything offline. It's all online, and it's, you know, on the order of milliseconds for 2 multiplications.
With this driving application of ECDSA that everybody wants to be threshold, do you think there are things that were helpful for MPC in general that just appeared for ECDSA that can now improve generic MPC?
That's a great question. So I think, and I've posed this to my students, this checking. So how does our approach differ from the Nigel Smart et al. That work? So they also observed that they can just use speeds. You can check the speeds exponents in the. You can check the speeds MAC in the exponent. However, they spend essentially twice as much time in the pre-processing to set up what they need for their MACs, and then twice as much bandwidth during the online phase in order to send these extra MACs. And so our observation is that in this particular application, I told you, because we have these 2 values, we don't have to do that, and we get this automatic MAC check. And so again, a natural question is like, can you create that artificial MAC check in the exponent for arbitrary circuits? So that's an open question. I've asked my students, they're all busy now, they don't listen to me, so if anybody here has an idea, I think that's a good problem to work at. So exactly your question, where does this help general MPC? And my take is that there's a new technique, a compressive technique for checking speed style or Badoza style max in the exponent that avoids the straightforward way that is already known for speeds in Badoza, which is just to create that extra thing and send it for each multiplication. And there they had that batch checking, but I think you can basically do that in the exponent more efficiently. That's the hypothesis. As for any other things, no. I mean, like this is a basically low-depth arithmetic circuit that we're trying to do MPC for, and we're all trying to find bespoke techniques for it. I think, I don't know where else these techniques help for other MPC problems.